Continuing from our last video where we had generated some of the names using this data set. Now let us first find a way to calculate the loss of the generation of words. Let's just add a code cell and let's create a loss variable and a size variable, both of which will be 0 at the moment. And then what we'll do is for name and for word names, name equals to and loss plus will be. Now we can either do this exact thing, no, not this, torch.log of p of 1 ix is 2 and then print the loss. Okay, yeah, size will also be incremented and then we'll print loss divided by size. Yeah, so we get this loss 2.454. This is the loss of the current model, which is not using neural networks at all. We are just generating names based on this data set on probability. So now let's actually make a neural network. First, what we'll do is we'll actually reuse this code. Where's this? Torch.ones, yeah, we'll actually reuse this code. Yeah, but what we'll do is we'll make some changes. First of all, we'll make our own data set access ys, which will be empty lists, and what we'll do is ix1 is integer, right? access dot append ix1 and ys x2. Yeah. If we print access of 5 and ys of 5, what we'll get is, yeah, so we'll get a very similar thing what we had done above. We had done this thing where for dot we expect e, for e we expect m, for m we expect m, for a we expect dot again. So what we have done here is we had mapped all the characters to their integers, right? What we'll do here is when the input is 0, which is dot, we expect 5, which is e. When the input is e, we expect m. When the input is m, we expect m. When the input is m, we expect a. When the input is a, we expect dot again. This is dot emma and this is emma dot. So this is the very same thing that we had done above, but instead of letters we are now using numbers. Yeah, so what we'll do is we'll convert access to torch.tensor of access and same with ys. Yeah, so now both of them are converted to tensor. Now what we'll do is, see, what do we know about neural networks? Neural networks are these architectures, right? Basically some inputs, then there's a hidden layer, and there are some outputs. Now what we want is, right now I printed this thing, right? Print access of 5 and ys of 5. Yeah, so when the input is 0 we expect 5. Basically when the input is dot we expect e, right? So let's imagine here that there are 27 of these blue circles and 27 of green circles. That is because there are 27 inputs and 27 expected outputs. So what we are doing here is when the input is 0, basically dot, we expect 5. So here what will happen is inside the neural network, when the 0th blue circle is on, basically this, let's imagine this is filled, we expect the 5th green circle to be filled. When the fifth blue circle is filled, then we expect the 13th green circle to be filled. That is how our neural network should work. So what we'll do here is we can't simply enter these values, right? 0, 5, 13. How do we tell the neural network to switch on the 0th blue circle or the 5th blue circle or the 13th blue circle? What we'll do is we'll encode access. X encoding will be f dot 1 hot and the input will be access num classes dot float. Yeah, so if we print access of 5 xenc, yeah, if you see access, every element of access has been encoded into 27 values, and whatever value is here will be represented as 1. So 0, 0th index is 1, 5, 5th index is 1, 13, 13th index is 1, again 13, 13th index is 1, and then 1 again. So first index is 1. What we have done here is converted this into proper inputs for our neural network. So when when we feed access like 0th input, this will be 1. Basically, the first circle or 0th indexed blue circle will be switched on. When the second input, which is 5, for 5 we have the 5th index as 1. That means the 5th circle will be turned on. This is how we have encoded xenc. Now what we'll do is we'll create a inner layer, the hidden layer. That will be w, which is equal to torch.rand, which will be 27 requires grad will be true. Now you should know what requires grad is from my previous videos, and we'll set the data type to be torch.float, float 32 maybe. Yeah, so if you print w of, let's say, just the first 2 rows, we'll get 2 rows of random floating point and numbers. Now what we'll do is we want the inputs to be multiplied by the weights, right? And what exactly we want is the first input should be multiplied by this, right? So what we'll do is here w at the rate, we'll do matrix multiplication, which is represented by at the rate w, and let's just print the first one. Yeah, so if you see, okay, let's print both the things, print this and print w of 2 also. Yeah, so if you see, w is this matrix, and the matrix multiplied xenc matrix multiplied by w is this thing. If you notice, since the 0 is turned on, the first row is unaffected. First row is the same, exactly the same. But the second row, if you see, it is changed. It is not the same. That is because the second row onwards till the 27th element is 0. So that is why we see a change in the second to 27. If we print till 27, we'll see different values compared to the original weights. So what we are doing is, whichever value, whichever index in xenc is 1, that is actually getting multiplied and updated, actually sorry, remains the same. Apart from then, all of the other indexes are getting changed. So what we'll do is we'll actually do it properly now. We'll first use g equals to torch.generator to increase the reproducibility dot manual seed of this, and then what we'll do is w will be generated again, torch.rand of 27, and it will be data type. Yeah, this is good. So now let's actually build the neural network. Let's run this again, and now let's do counts, or maybe logits equals to xenc w counts. Yeah, basically this. We'll also calculate the loss, which will be minus of torch.arange ys, and this will be paired with this will be xs, and this will be ys here, and this entire thing will be probs and .log .mean, and I guess it's good. We'll also add some tiny amount of w w squared dot mean. Yeah, that should be it. We should get a pretty high loss. Yeah, so we are getting pretty high loss, 3.36 compared to the original one, which was 2.45. So this is a pretty high loss. And if we generate the names right now, we should get very shitty names. Let's just generate the names right now. So the names that we are getting, let's generate 10 names. The names that we are getting are absolutely trash, because the neural net hasn't been trained yet. So let's actually train the neural net right now. Let's do w.grad equals to none, because we don't want the gradients to get compounded. And then we'll do loss dot backwards, and then we'll run this, and then we'll do w.data minus equals to w.grad. Yeah, so if you keep this in mind, the original loss is 3.363. If we run this again, yeah, so if you see, the loss is pretty high. If we run this now, yeah, so 3.363 is now reduced to 3.3572. So the loss is reducing, 3.3515. So yes, the loss is reducing. So basically what I'm doing here is, this is the forward pass. This is the forward pass. Here we also calculated the loss. Here we are setting the gradients, and here we are updating the weights. So let's just write a for loop for all of this, and we should get much better names after optimizing our model. What we'll do is, for an age 100, we'll do the forward pass. Forward pass, instead of printing, we'll do gradient setting, which will be this, and then updating the weights, which will be w.data minus equals to w.grad. And actually we'll increase this because the learning is very slow for this model. We'll print the loss now. We'll let it run for some time, and we should get a pretty low loss. 2.489. Let's decrease it and run it once more. Yeah, 2.4887. This is the final loss that we are getting. Now let's actually regenerate the names after we have trained our model. Now if we regenerate the names, yeah, so you see these names are much better than compared to this random model, untrained model. None of these names make sense because these are legit random letters. But if you look at this, these names make some sense at least. So, and as I told you at the starting of this video, since we are giving only one letter context to the model, the names won't be accurate, but still it does make some sense. So here we have it, the Bigram language model. In the next video, we'll try to optimize this model by adding more parameters and adding more context, such as 4 or 5 letters. And I'll see you there. Thank you.